Good afternoon, everyone. Thank you for coming to this week's CRM seminar. We have the pleasure of having Dimitra Karabali with us. She's an expert in high energy physics. She did her undergrad at the University of Athens in Greece, and then she did her PhD at Yale University with Thomas Appelquist, focusing on non-perturbative aspects of quantum field theory in 2+1 dimensions. And she's also done nice recent work on the quantum Hall effect in high dimensions. And today she will be talking about aspects of high dimensional quantum Hall effect. So please go ahead, Dimitra.
Hey, thank you very much for the invitation to give a seminar. Much of the work I'm going to talk about is in collaboration with Professor and Nair, who I think he's somewhere in the audience. This is a topic we have been working on and off for a number of years now. And I will mainly concentrate here on two aspects, effective actions and entanglement entropy, a topic that I know many of you are experts on. So let me start with some of the basic features of the standard quantum Hall effect in 2 dimensions. We deal with systems of non-relativistic electrons in a strong magnetic field. The main feature of this effect is, of course, the fact that the Hall conductivity is quantized, which is given in this formula, where it relates the external electric field and the generated current perpendicular to that field. And sigma is the Hall conductivity, which is given in terms of the fill-in fraction, which is integer for integer quantum Hall effect, and takes very special fractional values for the fractional quantum Hall effect. Now, in addition to this having a central importance in condensed matter physics, it has worked as a framework for many interesting ideas over the years. And for example, topological field theories, bulk edge dynamics, noncommutative geometries, and fuzzy spaces. So what I would like to do is, as I start with some of the basic features of the 2-dimensional quantum Hall effect, the integer quantum Hall effect, in terms of a single spectrum, and then the single particle spectrum, and then effective actions, and see how these generalize to higher dimensions. Okay, so one deals with a charged particle on a 2-dimensional plane or a sphere in a strong external magnetic field. So one has to solve the Landau problem. Well, the single body spectrum decomposes into distinct Landau levels, which are separated by an energy gap, which is proportional to the magnetic field. Each Landau level is degenerate. And in a particular gauge, the wave functions, the lowest Landau level wave functions, up to an exponential factor, they are essentially holomorphic functions. The many-body problem gives rise to the so-called quantum Hall droplets in the following sense. The degeneracy of each Landau level is lifted if we introduce a confining potential. And in reality, this is done by the actual boundaries of the sample. And so the electrons now localize around the minimum of this potential, but they're fermions, there is an exclusion principle. So as a result, they form incompressible droplets. And because of incompressibility, the low energy excitations of these droplets, the excitations form around the boundary of the droplet. They're the so-called area-preserving boundary fluctuations, which are the edge excitations. And these are collectively described in terms of 1-dimensional chiral boson, given in terms of this action. This was written down several years ago by Wen and Stone and others. I have a problem moving. Now, if one introduces, in addition to the background magnetic field, the constant magnetic field, the electromagnetic fluctuations, there is also bulk dynamics in the problem, which is described by an effective action, which is essentially a Chern-Simons action with an overall coefficient nu, which is the fill-in fraction. One can derive that by starting with a microscopic theory and integrating out the fermions. There is also the edge dynamics, which is now a gauged chiral action. Each of these actions is not gauge invariant, but of course the anomaly is cancelled if we consider both of them together, and the total action, as expected, is gauge invariant. Now the bulk action, the Chern-Simons action, captures the response of the system to electromagnetic fluctuations, in the sense that if we vary this action with respect to the gauge field, we find the current, and we reproduce the formula for the Hall conductivity that I showed you earlier. Now, recently there has been some interest in finding other transport coefficients, in particular, a question of how the system responds to stress and strain. So for that, one has to couple the microscopic theory to gravity, calculate the stress tensor, and the effective theory that comes out of this, once one integrates out the fermions, is of this form. This was derived by Banov and Gromov back in 2014. And this omega is the so-called the spin connection. S enumerates the different Landau levels. And we see here the coupling between omega and A, the so-called when Z term. And if one varies this effective action with respect to the spin connection, one finds a new transport coefficient, the so-called Hall viscosity. So now what I would like to mention and start explaining in more detail is that all of these important features of the original two-dimensional quantum Hall effect extend to higher dimensions, and the results are quite interesting. So the first attempt to define quantum Hall effect in higher dimensions was done by Hu and Zhang back in 2001, when they formulated the theory on the four sphere, and they introduced an SU2 magnetic field. And right after that, in collaboration with Parameswaran, we generalized this to arbitrary even dimensions by formulating quantum Hall effect on complex projective spaces. There are two important features that comes in this generalization. The first is, of course, one can introduce higher dimensionality. Second is it opens up the possibility of having both abelian and non-abelian magnetic fields. And I will say more about this later. In the case of non-abelian magnetic fields, these electrons, the charged particles, have essentially non-abelian internal degrees of freedom. Okay, so what I would like to do now is I give you a brief idea about how one derives the single particle spectrum, and then I will continue with the many-body problem. So the complex projective manifolds are 2K dimensional manifolds, which can be locally parameterized by K complex coordinates. The important thing is that they can be written as coset group manifolds. And it is this structure that makes it relatively easy to identify the single particle spectrum. Now, because of this factor UK, one sees that what I mentioned earlier, that one can have both a U1 and SUK background magnetic fields. Further, the Landau wave functions are functions of SUK plus 1 with particular transformation properties under UK. In the case of the two-dimensional problem, there are distinct Landau levels which are separated by energy gap. And each Landau level forms an irreducible SUK plus 1 representation whose dimension gives the degeneracy for each Landau level. And this is straightforward to do in this case. Because of the group structure, one can use an element G, which is in SUK plus 1 as a coordinate for the manifold. So the translations essentially correspond to group translations, where G and GH are identified if H is an element of UK. The wave functions are written in terms of Wigner-D functions, where these L and alpha are the quantum numbers within the particular J representation that Landau, the wave functions belong to. And one can define right and left translations. Now, because of this identification here, the right UK translations are essentially the gauge transformations of the theory. The costed ones are essentially the covariant derivatives that give the actual translations on this manifold, while the left ones are the analogs of the magnetic translations, which take us from one state to the other within the same Landau level. A few more things about the wave functions, how they transform under gauge transformations depends on the choice of the background field. And here I mentioned that we have the possibility of only a U1 magnetic field or UK magnetic field. Now, the field strength for the U1 magnetic field is proportional to the Kähler-2 form with a proportionality constant n, which is an integer. And this is exactly what happens also when we have quantum Hall effect on a sphere. So essentially this n, because sphere is CP1, so it's the smallest CP manifold that we can define. So this n is essentially the field of the strength of the magnetic monopole in the center of the sphere. But we also have the possibility of SUK background fields in addition to the U1, and the components of the field strength are proportional to the components of the Riemannian curvature, which are in the frame basis. These essentially are the SUK constants, structure constants. So in that sense, there are constant magnetic fields, abelian and non-abelian. Okay, just to summarize, so the wave functions for each Landau level form an SUK plus 1 representation J. The states alpha here, they carry the charge, a U1 charge proportional to n. And if there is an SUK magnetic fields, then they belong to some finite SUK representation, which we called J tilde. So this alpha, is an internal index that goes from 1 to the dimension of J tilde, while the else, this index L goes from 1 to dimension J and counts the degeneracy of the Landau levels. We can also write a Hamiltonian in terms of the covariant derivatives. The covariant derivatives are the coset right transformation, so we can write a Hamiltonian in terms of them. The lowest Landau level now is annihilated by this the right coset generators R, and this is the analog of the holomorphicity condition. This alpha now is the lowest weight state, so it's very easy to construct all the different wave functions. And also we can create higher Landau levels by acting with R+. Okay, so these manifolds give a kind of straightforward way to construct the full single particle spectrum. So now what I would like to do is I want to leave for a moment the CPK and deal with the many-body problem in a very general way and show you how one can find a universal kind of function that describes the dynamics within each Landau level. Okay, so suppose we have quantum Hall effect on a compact space M, then the lowest Landau level defines an n-dimensional Hilbert space. As I mentioned before, in the presence of a confining potential, one has a quantum Hall droplet. And let's say that K states are filled and n minus K are unoccupied. So one can write the density matrix for this ground state droplet in this way, where this is the lowest energy state, and as we go down, we increase the energy due to the confining potential. Okay, so the most general transformations one can do that leaves us within the lowest Landau level and preserves the occupancy number are n by n unitary transformations. So under time evolution, this rho 0 goes to another rho, which is via a unitary transformation. And these matrices, n by n unitary matrices, are can be essentially thought as collective variables which describe the excitations within the lowest Landau level. So one can write an action for this U. Okay, so the action of U now can be written like that. This is a matrix action, which leads to the evolution equation for the density matrix, which is as expected, where V now is the confining potential. So what I want to emphasize now that this is a universal matrix action that so far there has no explicit dependence on properties of space on which quantum Hall effect is defined, whether the background is abelian or non-abelian or any of that. However, one can introduce the space-time features the same way we do it for non-commutative field theory. Okay, so let me explain what I mean by that. Okay, so this is the matrix action I had before in terms of these collective variables U. So now what we do is we replace the matrices by the corresponding symbols. So a symbol is essentially a classical function which is derived by the matrix O by sandwiching it with single particle wave functions. So that's where the single particle spectrum is useful, to go from the matrix O to the corresponding symbol. Also, in going from the matrix action to the non-commutative field theory, we replace products of operators, products of matrices, with the corresponding star product of the symbols. And further, we replace the trace with the volume integral over the space where quantum Hall effect is defined. Okay, so this is the action for a non-commutative field theory in that sense, and I claim that this is the exact bosonic action which describes the dynamics of the lowest Landau level fermions. Now, this idea was used some time ago by Sekita in the two-dimensional context in deriving effective field theories. And as you see, this way, one circumvents the explicit integration over fermions, and also by the group of Das, Dar, Mandal, and Badia when they were talking about C1, C=1 string theory. Okay, so this is the exact bosonic action, but now I want to take a large n limit for that. So when one takes the large n limit, then this action reduces to an edge action and essentially a Vesuminov-Witten-like chiral edge action. And now I want to do that in the context of CPK. So I already have the single particle spectrum, so I can go from matrices to symbols using the single particle wave functions. Okay, so let's do that first for the case where we have an abelian background magnetic field. So in that case, U is written as C to the I phi, and the action now can be read, the non-commutative action can be written in terms of the symbol of I, which is just a boson field. And the large n limit, what we find is the following. We derive an effective action that lives at the boundary of the droplet, and it is written in this form. This is is reminiscent of what we had in 2 dimensions. In fact, if we restrict on the space to CP1, which is the sphere, this L, this operator L, which is a derivative, it's just a derivative, a tangential derivative along the boundary of the droplet. However, this is a higher dimensional theory. This is a droplet on 2k-1 spatial dimensions. And what happens in that case, of course, we have many directions which are tangential directions to the boundary of the droplet. But what happens, the theory selects a particular tangential direction, which is Poisson conjugate to the radial direction of the droplet. In this So although this theory is a higher dimensional theory, it can, because the propagation is along a particular tangential direction, it can be thought of as a collection of 1+1 dimensional chiral fields. Okay, so I will come back to that a little later, but this is an important point. And now we can generalize this for non-abelian background magnetic field. So in that case, the situation is a little more involved because now the symbol is a matrix valued function. Remember, the wave function now is a non-trivial representation of SUK of dimension n prime. So the edge effective action now is written in terms of a UN prime field, and it takes this form. Okay, now let me say a few things about that. If one neglects this term, which is in green, the rest of it looks like a two-dimensional Vesumino action. Okay, now, of course, because we are in higher dimensions, this is a three form, the manifold is t-dimensional, so we have to supplement with appropriate powers of the Kähler form. Okay, so this is essentially a version of Vesumino-Witten action in 2K dimensions. And this derivative now is just is the covariant analog of the derivative we had before. Okay, so this is vectorially coupled between left and right. So there are no anomalies involved here. So this is the edge effective action in the case of the non-abelian fields. Now, one can generalize this when there are gauge fluctuations present. Now, at the level of the matrix action, what we do is we replace this time derivative with a covariant derivative, where the script A is the analog of the gauge potential. So this is the matrix action involved. And as we did before, we can introduce star products and symbols to write it as a non-commutative field theory. But the question is, what is this script A? How is this script A related to the gauge fields coupled to the original fermions? Now, okay, so the way we answer that is the following. So if we look at this action is invariant under the following transformations. But on the other hand, we want to think of this as the action that gives the dynamics of the fermions with the gauge fields. So this has to be gauge invariant. So this action has to be gauge invariant under the usual gauge transformations, where the A hat here indicates the background magnetic field, and the unhatted one are the fluctuations around it. So this gives us a recipe of how to write script A in terms of the original gauge fields and the confining potential. So what we want to do is to find A script as a function of A's, of the gauge field, so that the gauge transformations induce this transformation that leaves that action invariant. Okay, so essentially, this is a kind of a generalized cyber-Witten map, which is extended now to non-abelian gauge fields and manifolds which have curvature. So now, if we take this script A as a function of A and put it in here and take the large n limit, what we find is that this action S splits into two parts, an edge part and a bulk part. So the edge part of the action is a chirally gauged Vesumino-Witten action in 2K dimensions. The bulk part is essentially a 2K plus 1 dimensional Chern-Simons action. Each one of them is not gauge invariant, but the sum together is gauge invariant because the anomaly cancellation was already built into the theory by the way we constructed script A in terms of the gauge fields. Okay, so so this is the effective action that gives the response of the system to gauge fluctuations. One can go further and ask, what about metric fluctuations? You see, the way we constructed these effective actions is by using the single particle spectrum of CPK. But now we are asking the question, can we deviate from the metric for CPK? And quick answer is yes, we can do that by using an index theorem. And here is, I want to just very briefly outline how we do that. So the lowest Landau level obeys this holomorphicity condition, but for complex manifolds, the number of normalizable solutions is given by the so-called Dolbeau index. Now, I'm not going to write the formula for that, but it is given as an integral of traces of curvatures and field strengths. And here is the strategy we follow. Now, if we have a fully filled lowest Landau level, the degeneracy of this level is given by this Dolbeau index. But if we think that each particle carries a unit charge 1, then this Dolbeau index is also the charge of the problem. So if we go now at the density level, the unintegrated quantity, then we can think of this Dolbeau index density, which is given in terms of gauge fields and curvatures and stuff like that, as the charge density of the problem. But we know that the charge density is given by differentiating the effective action, by varying the effective action with respect to A0. So we want this to be the Dolbeau index density. So what we do essentially, we integrate this expression to derive the effective action, which includes now metric perturbations. Okay, so we have very general results, but I only want to just give you a glimpse of a couple of cases. For example, in the two-dimensional case for CP1, what we find is the effective action for the lowest Landau level is of this form. This is what I showed you earlier, which was derived by essentially integrating out, starting from the microscopic theory, coupling it to gravity and integrating out the fermions. But here we have a different way to do that. And we have general results, which are true for and compact relations for arbitrary dimensions, higher Landau levels, and non-abelian magnetic fields. Here I'll give you one more example of, we go one higher dimension, CP2, in the case of abelian gauge field, and S is the S Landau level. So this is what we find. Again, we have couplings between the spin connections and the gauge fields. And of course, in this case, the curvature has an abelian part and a purely non-abelian part. And if we differentiate that with respect to A0, or we find the corresponding Hall viscosity in higher dimensions. And as I said, we have compact relations that give effective actions in arbitrary dimensions. So now I want to turn into the second part of my talk, which is about entanglement entropy. As I said, many of you are experts on this, so I won't go over too many details. So in order to find so are there any questions so far? Maybe I'm going too fast. Okay, so we divide the system into two regions, region D and its complementary, and define the reduced density metrics like that. So this GS is the many-body ground state. So the entanglement entropy now is defined in terms of these reduced density metrics like this. And for simplicity here, I will consider D to be the spherically symmetric region of CPK satisfied by this, satisfies this relation. So essentially, just to visualize it, if it was CP1, which is S2, this D is just a polar cap around the North Pole, bounded by a latitude angle theta. So this R is the radius of this cap and is tangent theta over 2 via stereographic projection. Okay, now the lowest Landau level fermion operator can be expanded like that, where these psi's are the single particle wave functions. Now we can define the following operators. We can define the operator AM, where we integrate the psi with the psi star, and similarly BM. And this lambda that enters in these expressions is essentially psi star psi integrated over the region D that we are interested in. And it is kind of straightforward to show that these sets of operators here form two independent fermionic algebras. And the original fermion operator C can be expanded in terms of A and B in this way. So essentially, B dagger generates the part of the wave function that is localized outside the region D, and A dagger is the creation operator that generates the part of the wave function which is localized inside D. So if we now trace with respect to B, what we find is that the reduced matrix rho is written as a 2 to the n by 2 to the n matrix of a block diagonal form. So the entanglement entropy takes this expression in terms of lambdas. Now, these lambdas can be also thought as eigenvalues of the two-point correlator, and this is something that was shown by Peschel in 2003. So if we write down this two-point correlator where Z and Z prime belong in the region D, are in the region D, then the eigenvalues of this operator are these lambdas. Okay, now for two-dimensional systems, gapped systems, there are general results that show that the entropy is proportional to the perimeter of the boundary of the entangling surface. And this is a non-universal constant. And there is also a universal constant gamma, the so-called topological entanglement entropy, which, however, is 0 for integer quantum Hall effect. So now this was for the integer quantum Hall effect. This was studied by Rodriguez and Sierra back in 2009. And in fact, they did confirm this. And they calculated for nu equals 1 this non-universal constant C, and they found to be 0.204. Now, more recently, there are other more general results on nu equals 1 on Kähler manifolds. This was done by Charles and Estienne in 2019. And what I would like to do now is see how these results extend in higher dimensions in the context of CPK, where we also have non-abelian magnetic fields. I want to mention that these results on Kähler manifold were only with U1 magnetic field. Let's look at the case of the U1 magnetic field first. Okay, so the lowest Landau wave functions are essentially the coherent states of CPK, these are the normalized wave functions. They're written in terms of these complex coordinates. These wave functions form an SUK plus 1 representation of dimension n, and this is the degeneracy of the lowest Landau level. And the volume element for CPK is this, which is normalized to 1. So these are all the ingredients we need to write down what lambdas are. So the eigenvalues lambda are of this form. This T0 here is written in terms of the radius of the polar cap, and they're essentially incomplete beta functions. each lambda s has a degeneracy, and the degeneracy factor is given by this term here. So now we can write down the entanglement entropy, which is this degeneracy factor times the entropy per mode lambda, which is of this form. Okay, so now for large n, it turns out that this is amenable to an analytical semiclassical calculation, and it is true for any k as long as k is smaller than n. So if I plot lambda now as a function of s, what we find is that there is a transition point right here in the middle, and this occurs at s, which is essentially n times t0. And at the transition point, lambda is half. And for s smaller than this s star, lambda is 1. And this corresponds to the modes that are localized within D. And for bigger s, then lambda is 0, which corresponds to the modes that localized outside D. So if I look at the form of the, cannot go back. Okay, if I look at the form of the entropy per lambda, you see that the support of that is only around the transition phase, because when lambda is 0 or 1, this edge is 0. Okay, so as a result, if I plot the graph of h as a function of s, there is a support only around the transition point here. And not only that, but this h is essentially a very a narrowly picked Gaussian approximation. The red here indicates the exact expression for h, and the dot is the Gaussian approximation. You see that kind of overlap. Also, I wanted to mention something about the graph for lambda, that this pattern, this graph is essentially the same for all k's. K equals 1 is the red, and k equals 5 is the blue, and they're identical. Now, because the entropy per mode is a Gaussian approximation, this allows us to do a semi-classical approximation for the entropy S. Okay, but I wanted to say one more, I have one more thing to mention here. So because the entropy has support only around the boundary of the entangling surface, only wave functions localized around the boundary contribute. So it is clear that the entropy eventually is proportional to the area for that reason. And using the fact that this is a Gaussian approximation, we can analytically calculate now the entropy. And what we find is indeed the entropy is proportional to the geometric area, with some coefficient here that depends on K. This is in very good, excellent agreement with the K equals 1 result, the sphere result by Rodriguez and Sierra. But what I want to mention here, that if we express the entropy not in terms of the geometric area, but in terms of the phase space area, we can find a universal expression for entropy which applies in any dimension. So here is what I mean by that. So the phase space, the volume of phase space is given by this, where omega is essentially the Kähler-2 form. So this nk over k factorial gives essentially the number of degrees of freedom. So if we define a phase space area which takes into account the number of degrees of freedom we have in the problem, you see that this factor here is essentially the factor that we have here. So the entropy then is read as expressed in terms of the phase space area, has an overall coefficient now that does not depend on K. Okay, so, and this formula applies for any dimension K. Now we can extend this
I have a quick question,
Sure.
if you allow.
Yes.
So this is very nice that you have this closed form universal formula for the area coefficient. Do you have a sense of what the deviation from the exact result? Because I gather the coefficient is not numerically exact. There is some small deviation due to the Gaussian approximation. So do you have a sense of?
Yes, it's
what's missing?
99.6%.
I'm sorry, how much?
99.6%.
Accurate.
The deviation is 0.004.
Yeah, and why is the deviation so close? Why is this approximation so close to the exact answer, but not quite? You know, what's the small thing that's missing?
Well, because the deviation, the result is very good because, I'm going backwards, I'm sorry. Okay, the result is very good because this is a very narrowly picked Gaussian. Okay, so the width of the Gaussian is 1 over square root of n. Talk about higher Landau levels, and you'll see that this entropy per mode is not Gaussian anymore. So I cannot do the same analytical semi-classical approximation. So it works for nu equals 1, but it does not work for the first excited level or nu equals 2. But why it does not work is interesting. So I want to show a little.
Because nu equal 2 for the IQH, morally is like 2 copies of nu equal 1. So
no, but you'll see why. I think it's interesting, and I left some room for that.
Okay, thanks.
Okay, so but the approximation is very good because it's a Gaussian approximation. And this does not happen for higher Landau levels, and I'll show you why. Okay, so this result here was only for abelian magnetic field. Now I want to very briefly say what happens when we have non-abelian magnetic fields. Now, as I mentioned, in that case, the wave function carry an SUK charge. Okay, so there are the lowest Landau wave functions are now SUK multiplets. And what happens is that for each of these multiplets, there is a distinct expression for lambda. So now we have n prime such lambdas, different expressions for lambdas. Okay, now calculating these wave functions, normalizing them, deriving lambda is long and tedious. But at the end of the day, when we take a large n limit, there are some very interesting simplifications. So essentially what happens when we take a large n limit is that the entropy is proportional to the entropy for the abelian problem with an overall factor, which is dimensional j tilde, which is this n prime here. Similarly, the degeneracy for the lowest Landau level at the large n limit is what it is for the U1 case times this n prime, the dimension of j tilde. Now, this dimension j tilde factor enters into the volume of the phase space, and the definition of the phase space area that I mentioned before. So as a result, at large n limit, the entropy, whether you have abelian or non-abelian magnetic fields, and for any dimension, takes this kind of universal expression. Okay, so for nu equals 1, we have this universal expression for any dimension and any kind of background field. So the question is, does this hold for higher Landau levels? Okay, so not for the reasons we said, but I wanted to show a few more details about that. So suppose now we consider the first excited level, first excited Landau level. Now, the degeneracy for q equals 1 is n plus 3. So it's more or less the same like for the large n limit is the same like the lowest Landau level. Now one can write down lambda, find a wave function, construct lambda. Now, if we plot lambda, the overall pattern looks somewhat similar. So certainly For small s, lambda is 1. For large s, lambda is 0 as expected. But there is a very distinct step-like pattern around the transition point. And one can trace this kind of step-like pattern on the fact that the first excited level wave functions have a node. In fact, if you do that for the qth excited Landau level, you'll find S plateaus around the transition point. Now, exactly because of this step-like pattern, if one plots the entropy per mode, one finds that there is a broadening of this entropy. So this entropy is not a simple Gaussian anymore. So it's for this reason that I cannot use the semi-analytical, semi-classical approximation that I did before. I can do the numerical calculation, and I find that the entropy for q equals 1 is 1.65, the entropy for q equals 0. Let's see what happens when we have nu equals 2, where both lowest Landau level and the first excited level are filled. Now, what happens, the problem now is more complicated. The 2-point correlator has two pieces, one for the lowest Landau level, another piece for the first Landau level. And one has to carefully diagonalize this operator because there are overlaps between the 0th Landau level wave function and the first excited Landau level wave function. Okay, so the diagonalization of this operator gives 2n plus 4 eigenvalues, lambda 0, 1, lambda 1, these are from the first and from the first excited level, but there are the lambda tildes. The lambda tildes can be written in terms of the lambdas for the lowest Landau level and the first excited Landau level, but this delta lambda shows the overlap between the two wave functions. Anyway, if we plot this lambda tilde, what we find is interesting. Now the step-like pattern disappears. So the lambda tilde plus and minus look very much like the one we had for nu equals 1, where there was no step-like pattern, but just displaced to the left and right. So as a result, if we write down the entropy per mode, so what we find is that the two entropies separately are Gaussian approximations, but we have to sum them. So now we have a kind of a two-mode distribution, which is not Gaussian. So for that reason also, we do not have the same analytical, cannot apply the same analytical semi-classical approximation for the entropy. Okay, so this gives you here a kind of a diagrammatic idea of how the entropies change. So the black one, it corresponds to nu equals 1, which is Gaussian. The first excited level, you see there is a broadening, and for the nu equals 1, the nu equals 2, then you have this double mode distribution. So as a result, I cannot use the same analytical approximation that I did before, where I replaced the sum by an integral using the Gaussian approximation for the entropy. So we can just numerically calculate, and we find that, of course, for this reason here, the entropy for nu equals 2 is bigger than the entropy for q equals 1, and that is bigger than the entropy for nu equals 1 with these numerical factors, but I do not have a good handle of analytical expressions for these numbers anymore.
And I'm sorry, if I may ask about the nu equal 2, is this the sum of two Gaussians? So
yes.
You can't.
Yes.
And that doesn't lead to a simplified form if you know that sum of two Gaussians instead of being
well,
Gaussian.
Okay, because it is important to know where the transition point is. And when I have nu equals 1, I know the S where the transition point occurs. That's an important step in calculating the entropy. and the width of the Gaussian and where the Gaussian is. For this one, I don't analytically know where this transition point is, at what S the transition point is. The reason I need that is the following. Let's look at this expression here. Okay, so H is a Gaussian approximation. So essentially this S is picked around where H peaks. So out of this integral, the main contribution comes from the S where the Gaussian peaks. But I know that for nu equals 1, but I do not know that for the case of nu equals 2. I don't know the analytical expression for that. Okay.
And there's no simple argument to guess that.
Okay, so there may be, I suspect if one tries hard, one can find some analytical expression. I just haven't pushed that very much. But I believe that there is a similar universal form for every Landau level. So if one if one can express the entropy in terms of the phase space area, then there is a universal expression, but with a different coefficient for each Landau level. That's what I guess, but I don't have a good analytical handle on this other than nu equals 1. Okay, so I'm at the end of the talk, so I wanted to give you a summary and a comment. So I talked about extensions of quantum Hall effect to higher dimensions. Now, several years ago, this would be a completely theoretical exercise, but it turns out that there are several groups that they have kind of realized four-dimensional quantum Hall effect in the lab, at least a way to simulate a fourth spatial dimension. So there are groups that have used cold atoms and the notion of synthetic dimension, where one goes a transition along the internal states of the problem, gives you mimics a transition along the fourth dimension. So hopefully one can see some of these effects for higher dimensional quantum Hall effect test them in the lab, maybe. Okay, so what I mentioned is that there is a universal matrix action, which is essentially a non-commutative bosonic field theory, which describes the lowest Landau level dynamics. And by taking the large N limit, one can construct effective actions where the anomaly free between bulk and edge dynamics, and this has been automatically built into the theory. One can also write down effective actions that involve metric perturbation by using the index theorem. And as I said, we have results for arbitrary dimensions. And then I talked about the entanglement entropy for higher dimensional quantum Hall effect on the context of CPK. And I showed you that at least for nu equals 1, there is a universal formula which is valid for any dimensions and any background fields, as long as the area is expressed in terms of a phase space area. Okay, now we want to make a comment that now when the boundary of the entangling surface intersects the edge boundary, there is an additional log contribution, at least in 2 dimensions. And that extra contribution is proportional to the central charge of the field theory that lives on the boundary. And this L is the segment that the entangling surface intersects the edge boundary. This was confirmed by Estienne and Stefan and William and his collaborators in 2019. And this was further extended to a 4-dimensional analog of quantum Hall effect by Estienne and collaborators in 2021. But as I mentioned, when I was talking about the effective action, the edge effective action we get in higher dimensions, this is expected because if we have only an abelian magnetic field, although we have a higher dimensional edge effective action, that is essentially a collection of 1 + 1 dimensional chiral fields. So we expect this to hold in any dimension. However, a more interesting, a more challenging question is, what happens when we have non-abelian magnetic fields? Because I showed you that in higher dimensions for non-abelian magnetic fields, we have the so-called Vesuminowitten version of edge theories in 2K dimensions, but the conformal properties of that theory are not obvious. So it's not clear what is the analog of C in that case, for example, and this is worth looking into. So I think I came to the end of my talk. Thank you very much.
Sharing, thanks for a very nice talk. A lot of interesting results and different systems, dimensions, manifolds. So it's now open to questions. So if anyone is curious about something, please feel free.
Could I ask a very naive?
Yes, John, and then Rufus. So John, please.
At the beginning, you distinguished between the integer and the fractional Hall effect, but I think most of your talk was concerned with the integral case. Is that correct?
All of my talk is about integer quantum Hall effect.
So my question is, what determines whether the effect is integer or fractional? And do you have any similar results for the fractional?
Well, integer quantum Hall effect is much easier to handle because the system is non-interacting. You can write down the single particle spectrum and from there find the many-body wave function. But in the fractional quantum Hall effect, the system is strongly interacting. So there are kind of trial wave functions that are like the Laughlin wave functions, but you cannot get them from first principles. Now, so the effective actions I discussed are essentially for the lowest Landau level and higher Landau levels, but integer quantum Hall effect. Now, there may be a way at the level of the effective action to introduce the notion of flux attachment to create effective actions for fractional quantum Hall effect, but we haven't systematically done that. So I think there is a way to extend many of the results to the fractional case, but what I discussed today is mainly integer.
There, for instance, an analog of the Laughlin wave function for non-abelian?
I think people write down, yes, trial wave functions for non-abelian cases too.
The Laughlin wave function, I'm not a specialist in condensed matter, but I have worked a lot about random matrices, and there's a close connection between random matrices and the Laughlin wave function that has to do something with integral systems, actually, Kaloger, Moser, and so on. So I mean, the Laughlin wave function happens, at least in the ground state, it happens to coincide with the GUE distribution as far as the density is concerned. So I was wondering if there's any non-abelian analog of that.
But as I said, the results that I have presented are, part of the way we constructed the effective actions from the matrix action uses the notion of the star product that needs the one particle spectrum. That is something, so that is kind of uses the fact that we have a single particle spectrum, the system is not non-interacting. I'm sure there are ways to generalize, it just, I don't have a very good answer to, specific answer to your question.
Okay, so maybe we can go to the next question also. So Rufus.
Yes, very nice talk. I was just wondering if disorder plays any role, because one of the key things
I'm sorry, I didn't hear. I'm so sorry.
Disorder. So the conventional quantum Hall effect, as you mentioned, the Chern-Simons term gives you a quantized Hall conductivity, but to have the plateaus, you need disorder to have localized states. So I was just wondering, in these high dimension versions, presumably you have quantized Hall conductivity, but would you have plateaus in these cases, and would you need disorder to have such physics like you do in the conventional one?
Yeah, so for the two-dimensional case, you have disorder, but this is, so we focus on what happens at the plateau itself. So we kind of extend this to higher dimensions. So we assume that we have these plateaus and we ask, what is the response of the system to electromagnetic fluctuations, let's say? So this is the role of the effective actions that we find. If we take those effective actions and vary with respect to the Gates field, we find the current, and from there you can get the Hall conductivity. Now, of course you can think of the quantization of the Hall conductivity, thinking about electronic band structures and stuff like that. But okay, so let's say that I haven't thought very much about the role of the. Certainly, it's important in two dimensions, and I'm sure it will be similarly important in higher dimensions.
Can I make a comment or ask a question?
Yes, of course, Professor Nair.
The comment pertains to disorder. The answer would be yes, definitely you need disorder. If you look at experimental realizations of high-dimensional quantum Hall systems, you do need localized states. You would need disorder. Recall that in two dimensions, on top of that, the Hall conductivity is related to the Chern number, the Berry curvature, associated with the Berry curvature of the band. So there will be a similar structure. That second structure we do have in high dimensions. The question of disorder depends on the experimental realization, I think. And I would imagine it is needed. But since there is so far no clear experimental realization yet, people are trying, I don't think it's entirely clear. The question I had was kind of related to the question about the Gaussian orthogonal ensemble that was mentioned. I mean, let me just ask it as a question. If you look at the matrix ensembles, if you just take the large n type of limit, you do get things that resemble Laughlin wave functions. Essentially, I assume coming out of the Vandermonde type determinant. On the other hand, if you take the large n limit subject to a certain number of conditions, roughly speaking, preserve certain block diagonality properties, it may be possible to get the fully non-abelian Laughlin wave functions. So if anyone has tried this in the math literature, perhaps the answer is no. I don't know. Is the question clear?
I'm not sure if you're addressing the question to me or to the speaker.
Yes, I'm addressing to you.
Yes, to you.
Well, there are, of course, many non-uniform limits. I mean, non-Wigner limits that are also studied in, for instance, tri-diagonal matrices and so on, or blocks. And there are some universality results, but I don't know if one gets anything like a non-abelian analog of the Laughlin wave function. Maybe someone knows that. I don't happen to know it.
Yeah, because my guess would be that kind of the block form large and limit would be what is needed, actually. So more restricted than just a naive large and limit of Wigner.
Yes, that sounds like a very reasonable idea.
Yeah.
May I also slip in another one? But this is only if there's nothing else more urgent.
Yeah, please, John.
So when we talk about experimental, as far as I know, unless we're not talking about a condensed matter laboratory, we don't have a non-abelian gauge theory to just experiment with. So what does it actually mean when you're speaking about a non-abelian magnetic field? Can that be created somehow in the laboratory?
Experimentally, well, in two dimensions. Well, I don't know. Maybe experimentalists can talk about that.
So yeah, maybe some analog system. Obviously, it's not like some SU2 from the standard model, but in some analog system, maybe people can engineer something that maps to this non-abelian quantum Hall problem. I guess this is always possible. I don't have the details, but I wouldn't be surprised if someone told me that there exists.
Even in 2 dimensions, you mean?
This is not real. It's not really an answer. It's just, it's possible in analog systems to create almost anything you want. One example of non-abelian gauge field is the Berry connection in a band insulator, but it's not as if like you can control that. It's given by the band structure and the eigenstates, but maybe people have some clever ways in cold atomic systems to put some non-abelian gauge fields. I know they have some clever tricks in cold atom systems. But maybe I have a quick question, very naive, but it's been burning me, because you have this universal formula for the area law in terms of the phase space. We tried to apply it to a fractional quantum Hall effect with abelian gauge field, say filling 1/3 in 2 dimensions, the canonical Laughlin 1/3 plateau. And that formula give you something as a guess for the fractional case, or the phase space area, if you work with fractional filling, it's ambiguous and you can't really make any prediction. Can I use this formula and sort of go away from the place where it was derived and try to apply it for fractional fillings, or it's
Well, of course, fractional filling is more complicated because you expect, you don't have only local correlations that are important. There is the topological.
No, I know, but I mean, the boundary law coefficient, though, is very local. So I'm just trying to abuse the nice mathematical result you have and try to maybe the guess for the fractional quantum Hall effect, but I'm not sure how it would work. I mean, it's a very naive question. It's like, can we try to abuse this result in the fractional case, where the area law coefficient is very local, right? I mean, irrespective of the system, this probe is very local physics because it's the boundary law coefficient.
Yes, this would be based on the local physics. Of course, you would have an extra universal topological term.
I guess the question is, can I convert this phase space area in terms of a geometric area, but for the fractional case, is there something new, or because this formula, it looks general? Yeah.
Go ahead. I think this may be the same, but I hesitate to say that because I haven't looked really in detail for fractional cases. This is,
Let's say I just want to try to convert the phase space area. I'm just not really familiar with this A phase space. Like, what would the conversion be between the phase space area?
That is okay. So the phase space volume is this. So once I have a volume, it's very easy to write down what is the phase space area.
But what's the?
This is for the filling. This is okay. So these are the degrees of freedom. Essentially, this is the Keller form. This is the number of degrees of freedom. But this is true if I have a field, a nu equals 1 field case. Now, the number of degrees of freedom, if I have a fractional case, is not the same. In principle, however, if I know the degrees of freedom, how many states are filled, I can write down a phase space volume and derive the phase space area. All this construction has been done using the nu equals 1 ground state, so this one. So I cannot say how things will change if I use Laughlin wave functions. Maybe just an overall factor, depending on nu equals 1/3 or something like that, maybe. But I'm not 100% sure. I haven't done that.
No,
but
I agree. I mean, it's abusing the result for sure. But I mean, maybe it's like, whatever number you would get from abusing it, you can compare it to the real number and see how big the deviation is, how far is this picture from what's happening at some fractional filling.
Yeah.
Just we have so few comparison points for fractional quantum Hall states, even for the Laughlin. They're simple wave functions to write down, but they're very hard to extract, even the boundary law coefficients. So we don't have really much expectations. Like we don't know how it should scale the filling, you know, like is it linear? Is it, you know, some crazy non-monotonic form? And when you go to the fractional fillings, integer fillings, yeah, things.
Yeah, you see, the fact that this result depends on the phase space area is kind of reasonable in the following sense, because the fact that it depends on the area has to do that the entropy has contributions only from states that are localized around the boundary of the entangling surface. But there is an extra factor, which is how many states are localized around there. That's what the phase space area captures, not just the area, but how many modes are around there. So I think that fact should also be true for the Laughlin wave functions. So it could be that this factor will be just normalized by the appropriate nu if we have a fractional quantum Hall effect. But okay. I don't bet on this because I haven't done the calculation, but maybe. But that's the new thing about the phase space area, because it takes into account how many modes you have, not only that there are the modes that are localized on the boundary, but how many of them.
Oh, yeah, it's interesting. I'll think about this. Tempting to try it and compare it with what people get using the wave function.
Yeah, now you had mentioned, of course, in the message you had sent me at some point about if you look at the entanglement spectrum, the dispersion relation you find, and that I find it kind of not puzzling, interesting, because I would expect that because of the step-like patterns, you would not be able to find a very simple dispersion relation for any odd excited Landau levels, or even that's what you had mentioned, if I remember well, that the dispersion around here goes like k to the third for odd excited Landau levels. So that is.
Yeah, but these are excited states, and somehow this entanglement cut mapping to a physical, like a real physical boundary, there it's more murky, it's not so clear. For ground states, you know, the spectrum is linear and sort of matches what you expect from the physical boundary cut, you know, Carl fermion. But here for excited states, it's much less constrained than a ground state. So yeah, I think people don't understand really.
No, so for each qth level, as I said, at the qth excited level, you expect q such steps. So so I find it interesting that for any q which is odd, the dispersion is the same.
Near the middle.
Near the transition point,
the maximal entropy contribution, lambda's 1/2. Yeah, I mean, we don't have a proof, it's more of an observation. I think on this note, we're gonna let you go because we have many questions at this point. And thanks again for coming over by Zoom.
Yeah, thank you very much for inviting me.
For closing this series of seminars. This is the last seminar.